चलो ठीक है. अच्छा, calculus I'm going to try and balance this equation, ठीक है. अब फिर I'm going to try and make half equations out of it as well, ठीक है. तो this one MnO4 minus 1, ठीक है. Let's try and do this. MnO4 minus 1. So what's the oxidation state of Mn over here? Yeah, what's the oxidation state?
+7.
ठीक है, MnO4 minus 1, that's +7. And MnO2 में what is the oxidation state of MnO2?
+4.
ठीक है, that's +4. अच्छा, T over here is definitely 0. TO3 2 minus, ठीक है, what is the oxidation state?
Also +4.
ठीक है, so that's +4. अच्छा, so anyway, so who gains, who loses electrons? It's Mn that's going from +7 to +4. So that means it gained how many electrons? 3 electrons. And T is the one that's going from 0 to +4. So that means it lost 4 electrons. ठीक है. So okay, what number would I multiply both with? Yeah, what's the number? 3 electrons being gained, 4 electrons being lost. क्या होगा, anyone? Talal, क्या होगा? What's the number? Akshita?
4.
ठीक है, so this will be multiplied by 4. And this will be multiplied by 3. So I should have, ठीक है, so I should have 4 Mns. And I should have 3, ये delirium है शायद, I think. So 3 TEs, right? So this part is balanced. The electrons gained and lost are balanced. The only thing that's unbalanced now is ये जो OH and water, right? You just go and balance it. So that's the only thing left. So they're going to be balanced the normal way. So how would you balance those? But क्या होगा? How many oxygens you got? You got 2 or 3? तो कितने होंगे? That's 6? नहीं, 5? नहीं, that's not 2. That's 8 plus 9. कितने oxygens count कर लो? You got 4 plus 4, that's 16 on this side. And there's a certain number of oxygen over here. ठीक है, I have no idea के मतलब अभी I have no idea के what should X be, ठीक है. And I've got oxygens over here. That's 8. ठीक है, so I've got 8 oxygens. Plus I've got 3 into 3, कितने हुए? That's 9. And plus I've got, so how many is that? That's 17. Plus if I add this 1 oxygen over here, water के अंदर, that's going to make it 18, right? So I've got,
Yes, sir.
I've got a total of 18 oxygens. So X क्या होगा? I guess that's going to be 2, right? ठीक है, is that clear? वो oxygen will get balanced. Is that clear? Oxygen is balanced. 16 plus 2, that's 18. 4 2 is 8. 9, that's 17. 17 plus 1, that's 18 as well. Is that clear? And your H's are also balanced. H kitne, that's 2. And H over here, that's also 2. Is that clear?
Yes, sir.
So then convert this equation into 2 half equations, the oxidation equation and the reduction equation. So I'm going to write the reduction equation. The reduction equation is the Mn equation. It's MnO4 minus 1. It's MnO4 minus 1. And it's gaining how many electrons? 3 electrons. And it's forming MnO2. So that's my reduction equation. And the oxidation equation, I'm not adding the balance equation. I just have writing the half equation in the simplest form. MnO4 and gaining 3 electrons to form MnO2. And it's not balanced. Remember, it's not balanced. The oxygens are not balanced over here. To balance out the oxygen, we're going to use what we're going to use. I mean, the equation has these OH ions and water molecules that are kind of redundant. So we'll be using those to balance it. I said the oxidation equation. What's your oxidation equation? So that is Te, and that's turning into T. It's losing how many electrons? It's losing 4 electrons, sorry. Okay, so we've got Te, it's losing 4 electrons to form TeO3, 2 minus, and it lost 4 electrons. So by reduction or oxidation equation. The only problem is that these are not balanced equation. At least the oxygens in the equation are not really balanced. And the only extra thing I have in the equation to balance them with is OH ions and water molecules. So I'm going to just try and add OH and water just to try and see how I can balance it. So in this equation over here, I've got 2 oxygens and I've got 4 oxygens on this side. Remember, I'm not going to touch this. I'm not going to disturb this. So all I need to do is I need to somehow use these two to balance this equation. So my oxygens are balanced. So how could that be? Okay, if I'm just going to do some trial and error. So if I add इस साइड पे ऑक्सीजन बढ़ाना है ना, so if I add like 2 water molecules, right? So is my oxygen balanced now? 4 oxygens, and there are 4 oxygens. But the trouble is that the H is not balanced. So I need 4 H's on that side. So now that's a problem because I can't just have 4 H's. So what I can do is, let's try add OH ions on this side. You can remember just random trial and error. So if I add OH ions to this side, and I add 2 OH ions. So be aware. So what's happening now is, I think we've got a problem. It's going to be very hard to balance it with OH and H2O. Can anyone else try as well? Because if I add OH ions, the oxygens are balanced. But the problem now is that I still have 2 H's to cover on the other side, so which is still going to be problematic. So what I can do is I can think of, I've got oxygens over here. So if I try adding water molecules on this side. So now what do I have? Let's say I add 2 water molecules. So I've got 4 H's. कितना हो गया? This is this is the only thing that's extra, right? OH and H2O. So I'm trying the other thing, which is that if I add, is there something missing in the equation? Just 1 second. TK, the middle part, it should not be disturbed. So let's, एक दफा ना we'll try and balance this way. So water right now, right? So अब क्या हो गया? You got 2 oxygens, 4 oxygens, that's 6 oxygens, right? So I've got 6 oxygens over here. And I've got 4 H's as well. Right? What do we have? Now I think it's getting balanced. What do I have over here? I've got 2 oxygens over here already. So I need to cover, I need to make up for 4 oxygens and 4 H's, right? So 4 OH ions. Now it's balanced. Is this clear? Okay, this equation is now balanced in terms of oxygen and hydrogen. Is this part clear?
Yes, sir.
Right. The trouble was that if I wanted to make the half equation, the half equations were not coming out to be balanced. So I had to somehow add OH and then H2O to balance those half equations. Try doing the other one as well. So try doing the other one. So I'm just going to, remember I need to, this equation I'm not going to touch. I just need to balance this oxygen by adding OH ions and water. So if let's say I add OH ions over here and I add water molecules to the other side. And if that doesn't work out, I'm going to do the other way around. Remember, my task is I'm not going to touch the middle equation. I just need to balance the oxygens, right? So if I have 3 oxygens over here, so there should be what, 3 OH ions, right? But then the trouble is that I'll have 3 spare H's, right? So can this be balanced or not? Let's say I have 3 water molecules on this side. So that gives me a total of what, 6 H's? And it gives me a total of 6 oxygen ions. Like 3 oxygen ions over here, 3 oxygen ions over here. Now it's going to get balanced. This is going to be 6 OH ions. Now this equation is balanced. Okay, is this clear?
Yes, sir.
Okay, but बाकियों clear है? Akshita, is this clear? Ibrahim, Jody, Meher?
Yes, sir.
So just remember, okay, this, I mean, we're going to keep on doing this. Okay, the whole chapter is about this. It's balancing redox equations. Sometimes, very rarely, this is not that important. Very rarely, they might ask you to make half equations from an equation that's already given, which is not that difficult. It's only the trouble is that you can figure out the reduction equation, you can figure out the oxidation equations, but they're not going to be balanced. So with the remaining elements which are present in the equation, you're going to use them to balance those equations. And that would be slightly tricky. Okay, that would require a bit of trial and error. So that would be a bit of time. I mean, it's going to be a bit time consuming if you're doing that. I said, I'm moving on. Okay, we'll in this chapter, we'll be doing this a lot. Okay, we've already covered balancing redox equations. So we'll continue to do that in the rest of the chapter. So now the important thing is, so we're gonna start with the A2 topic now. Now the important thing is that when you have a redox equation, so far in AS, what has always happened is the equations were always given to you, that it's a redox equation, and you were being asked to figure out who's getting oxidized, who's getting reduced, which one is an oxidizing agent, which one is a reducing agent, or you were being asked to balance those redox equations. Okay? But the equation was always there. So now we're going to learn how to make redox equations. And that requires standard electrode potentials. So we're going to learn how to construct a redox equation from scratch. We're going to try and figure out who's going to gain electron, and who. So we are the one who's going to decide who's going to gain electron and who loses electrons, who gets oxidized, who gets reduced. So for example, if I give you a reaction of tin2 plus reacting with Pb2 plus. So at this point, I have no idea what's going to happen. I have no idea who's the one who's going to lose electrons or gain electrons, and how many electrons would be lost and how many electrons would be gained. We have no idea at the moment. So how do we develop a system where we're able to figure out what a redox reaction is going to look like in this case? So you construct electrodes. The first type of electrode is, the electrode helps us decide whether the substance likes to gain electron or whether it likes to lose electrons, and whether it likes to gain 3 electrons or whether it likes to gain 1 electron. So this system that we're going to build, that system is going to decide how the reaction is going to happen, or predict how the reaction is going to happen. So the first type of electrode is a metal and aqueous ion electrode. So for example, if you have to decide between a metal, whether it wants to lose electrons, gain electrons, what does it like to do? For example, I've got 2 metals. So I've got sodium. So can somebody tell me, what does sodium like to do? Does it like to lose electrons and turn into ions, or does it like to gain electrons and turn back into? क्या होगा? Likes to lose electrons or gain electrons? So sodium really likes to lose electrons, and it very strongly likes to lose electrons. So it's very reactive. It strongly likes to. Which vice versa means that it doesn't like to do the opposite. That it doesn't like. It doesn't like to gain those electrons. So it likes to lose electrons very, very strongly. So we're going to build an electrode using sodium. We're going to take sodium, and we will place that sodium into a solution that contains sodium ions. So there's a sodium metal. Remember, this is a very simplistic diagram. So you'll just be expected to draw very simplistic diagrams, and you'll put that or place that sodium metal into a solution that contains sodium ions. For example, it's a solution of NaCl, aqueous. And it's going to have a concentration of 1 mole per dm cube. So what's going to happen? What's going to happen is that we already know that sodium likes to lose electrons. So sodium will immediately start, losing a lot of electrons. And it will start turning into ions. It will start to dissolve, right? So there's going to be a lot of sodium ions that are going to be produced. Ye clear? Okay, a lot of sodium ions are going to get produced. Because we already know that sodium likes to lose electrons. So a lot of sodium ions are getting produced. Where are all the electrons going? They're not going anywhere. It's a metallic rod. It's got a delocalized electron cloud, and that delocalized electron cloud is increasing in size. Why? Because sodium is constantly losing electrons. It's constantly dissolving into ions, and it's leaving those electrons behind on the metallic rod. So the metallic rod, the delocalized electron cloud in the metallic rod, its negative charge increases. More and more electrons are getting produced. So sodium will dissolve even more. More sodium ions are going to get produced. And when more sodium ions get produced, the metallic rod, there's going to be more electrons on the metallic rod. Okay? So is this part clear? That sodium is dissolving. Is that clear?
Yes, sir.
Okay. So, Tala clear? Akshita, is this clear? Everyone else?
Yes, sir.
Achha, but this is not going to happen endlessly. A point would come, I mean, sodium is dissolving. It's producing more and more ions, and more electrons are being left behind on the metallic rod. So there's a negative charge that's building up on the metallic rod. And that negative charge is probably going to be very large because sodium is very reactive. So sodium likes to lose a lot of electrons. So there's going to be a lot of electrons on the metallic rod. But this process will not happen endlessly. A point would come when the negative charge on the metallic rod, there would be so many electrons on the metallic rod, the negative charge over here would become so large that at that point, the sodium ions, because of the large negative charge, the ions are going to get attracted back to the electrons. Right? A point would come that the metallic rod would be so negative and it will have such a large negative charge that it will start attracting the sodium ions back again. And that's when you will have a reversible reaction. So it's going to have a, so it's at that point that you're going to have a reversible reaction. Is that clear?
Yes, sir.
Tiki, is Sarung
Yes,
clear?
sir.
Okay. So again, just a brief overview. Sodium likes to lose electrons. It will start dissolving. It will start producing a lot of sodium ions. A lot of electrons would be left behind on the metallic rod because sodium really likes to lose electrons. And but the process will not go endlessly. It's not going to go unchecked. It's not going to just keep on happening. They would, at a time would come when there would be so many electrons on the metallic rod that the negative charge would become very large and it will start attracting the sodium ions back again. So that is the point when when a reversible reaction gets established and the amount of electrons on the metallic rod becomes constant, or the amount of charge that has built up on the metallic rod, because it's at equilibrium now. When the rate of forward reaction and the rate of backward reaction becomes equal, so that means the reaction is now at equilibrium. All you need to do now is you just need to measure the voltage. That's it. That's the only thing you need to do. So all you need to do is you take a voltmeter and connect it with this. And so attach a voltmeter somewhere over here. So simply measure the voltage at this point. And that's known as your E naught, which is known as the standard electrode potential. For sodium, this value is already calculated. It's 2.71 volts. So a negative voltage indicates that sodium really ended up losing electrons. It made the electrode very negative. The electrode had a very negative charge. And why did it have a negative charge? Because sodium really liked to lose electrons. So a voltage over here would give you an idea about what the substance is doing. So a very low voltage indicates, or a low potential, or a negative potential, it indicates that the substance likes to lose electrons. That's why your electrode was very negative. Is that clear? Okay. Is this part clear?
Yes,
Clear?
sir.
Yes, sir.
Achha, so that's the first part. So if a substance likes to lose electrons and lose a lot of electrons, the electrode will become very negative and the voltage will become very negative, and that kind of gives you an idea about what the substance likes to do. Similarly, if I have another metal aqueous-ion electrode, and this one, it's an unreactive metal. Okay, for example, I've got a metal aqueous-ion electrode, and this one is a copper electrode. So in the case of copper, I know that copper, it doesn't really like to lose electrons because it's very unreactive. Why is it unreactive? Because copper has a very strong attraction for electrons. Okay, transition metals normally the nucleuses attract electrons very strongly. So they don't like to let go of the electrons. So it doesn't like to lose electrons. The reverse, I know that copper ions, on the other hand, they actually like to gain electrons. So remember this small thing, which is that if the metal is unreactive, its ion is actually more reactive. Its ion is very reactive. Remember, it's the opposite. Okay, make sure you remember this, that if the metal is unreactive, that means it doesn't like to lose electrons. That means the ion is going to be very, very reactive. The ion would very strongly try to gain electrons back. So I'm going to construct the electrode. It's going to be a similar electrode. I'm going to take a copper. Okay, I'm just going to copy paste that one. So it's the same type of electrode. The drawings are very important. So in this case, just let me change. So now in this case, the things would be slightly different. So you'll have copper ions in the solution. So this one. So there's going to be a copper electrode. It's a metallic rod with delocalized electrons. And the solution is going to have a lot of copper ions. 1 mole per dm cube. Where are the copper ions coming from? Maybe it's a solution of copper sulfate, aqueous, that you've added. It's 1 mole per dm cube. So it's probably a copper sulfate solution with 1 mole per dm cube concentration. So now I know that copper doesn't like to lose electrons. I know that copper doesn't like to lose electrons. In fact, it's copper ions that actually want to gain electrons. So what they'll try to do is they'll try to gain electrons, right? So the electrons will be gained by copper ions. Copper ions will start gaining electrons. And they will start forming copper metal. So if the copper ions are gaining electrons, the electrode over here will become electron deficient. It's going to have positive charge. More and more positive charge will start building up. Why? Because all the delocalized electrons in the metallic rod, they're being gained by the copper ions. Is that clear? Clear, Saroko? Is this clear? Zaina, is this clear? Jody, is this clear?
Yes, sir. Thank you.
Yes, sir.
Okay. Again, this will not happen endlessly. A time would come that the positive charge over here that's building up on the metallic rod, that becomes so large that it wants its electrons back. So when it wants its electrons back, it's going to take copper atoms and it will start pulling electrons back from it. So it's not going to go endlessly. Copper ions will initially gain a lot of electrons because they like to gain electrons, but that would make the metallic rod very, very positive. And so it would make the metallic rod, 1 second. So it's going to make the metallic rod very positive. But a point would come that it will become so positive that it will take the copper atom and start pulling electrons out of it. So it will start forming copper ions back again. So a reversible reaction gets established at this point. So over here, this reaction, it turns reversible and it becomes an equilibrium reaction when the rate of forward reaction and the rate of backward reaction becomes equal. It is at this point that the charge on the electrode will become constant, because the amount of electrons being gained and the amount of electrons being lost, that's the same now. So the charge once at equilibrium becomes constant. The E naught has already been calculated. The electrode potential, that's for copper, that's plus 0.34 volts. So that's a positive potential. So what a higher potential indicates that it's what does it tell you about the substance? It tells you about the substance that a higher E naught shows that the substance basically likes to gain electrons. Is that clear?
Yes, sir.
So the substance really likes to gain electrons. And that's it. So that's your two basic electrodes. Now, and the whole summary of the chapter, or the main point of the chapter is, this E naught gives you a lot of idea about what the substance wants to do. And the whole summary, the basic point of the whole chapter is, if you're getting a higher E naught or a positive potential, that indicates that the substance, or whatever the substance is, whether it's an ion or a metal or whatever, it likes to gain electrons. It likes to get reduced. A lower potential or a negative E naught indicates that the substance, it really likes to lose electrons. That's why it's negative potential, right? It likes to lose electrons. And that's it. That's the key of the chapter, of the entire chapter. Who wants to gain electrons? Who wants to lose electrons? Is that clear? So sodium wanted to lose electrons. It ended up producing a lot of electrons on the electrode. That's why the electrode became very negative. That meant a lower potential. It liked to lose electrons. Copper, on the other hand, did not like to lose electrons. Instead, it wanted to gain electrons. The ions in the solution wanted to gain electrons. So the electrode became electron deficient. It became very positive. So if the substance likes to gain electrons, it's going to make the electrode very positive. So is this clear? The main key of the chapter. That's the main point of the chapter. Is this clear?
Yes, sir. Thank you.
So that's the first thing. Just always remember, higher potential gains electrons, lower potential wants to lose electrons. That's the first thing. Now the detail is very important, because the first thing is they're going to ask you about drawings. So this over here is our first type of electrode, a metal aqueous-ion electrode. So you should be familiar with how to draw this electrode. It's just a metal, and you put it into a solution that contains ions of the same metal, right? That's the first type. Now, the second type is it might involve a gas. So electrode number 2, what's the drawing of an electrode that has a gas? So what if you have a gas that's in equilibrium with aqueous ions? So how would that electrode look like? So this one. So for example, a gas electrode would be like this, that let's say I want to figure out whether Cl2 likes to gain electrons. I said, what does Cl2 want to do? Does it like to gain electrons, or, I mean, can somebody tell me, does it like to gain electrons and form Cl-1? Or does it like to do the opposite? क्या होगा? Does anyone any idea? Minahil, क्या होगा?
I think it likes to gain.
Yeah, it likes to gain. ठीक है, Cl is very reactive. It's a very reactive non-metal. It always likes to gain electrons, right? It's a very electronegative substance as well. Has a strong attraction for. It's got a very strong attraction for electrons. So we know it likes to gain electrons. So it's probably not going to try and lose electrons. The ions are not. I mean, the reverse is probably not going to happen. So we're going to check this out using an electrode. So how would you draw an electrode? Because one of them is a gas and the other one is aqueous ions. So how would the electrode look like? So the electrode will have a gas jar, obviously. So there's going to be, one second. So there's going to be a gas jar. And my gas jar over here. Okay, so I've got a gas jar, and I'll be adding Cl2 gas from some point over here. That's, yeah, that's good. And this one as well, just a second. You remember the drawings are very important. So here's your gas jar, and there's Cl2 gas that's entering the gas jar. And it's going to be at 1 atmosphere pressure. Remember, everything is happening under standard conditions. I'm going to write that at the end. So everything is happening under standard conditions, 1 atmosphere pressure. And I'm going to place this gas jar into a solution that contains Cl ions. So let's say there is this solution, and it's got a lot of Cl ions. Maybe it's HCl 1 mole per dm cube, or NaCl 1 mole per dm cube. Let's say it's NaCl aqueous, and it's 1 mole per dm cube. You can remember standard conditions is that it's got to be 1 mole per dm cube. I said, now if Cl2, now we've got a problem because there is no electrode. If Cl2 wants to gain electrons, like over here, we know that Cl2 likes to gain electrons. Where would it gain those electrons from? There's no place to gain those electrons. So you have to introduce an electrode, because both of them are non-metals. One of them is ions, the other one is, Cl is a non-metal. So what you're going to do is you're going to add a metallic electrode. And this metallic electrode has to be an inert electrode. So it's probably going to be made out of platinum, because platinum itself will not react. So not only is platinum an inert electrode, but it's also a catalyst as well. What it does is it speeds up the reaction. So platinum is only used as an electrode. If somebody wants electrons, it can take those electrons from platinum, because it's got a sea of delocalized electrons. If somebody wants to lose electrons, it's going to give those electrons to platinum. Now, what's going to happen? We know that Cl2 likes to gain electrons, right? So that means platinum will it's going to slowly start becoming electron deficient, because chlorine is very reactive, and chlorine wants to gain electrons. So it's going to go to platinum, and it will start gaining electrons, and a lot of Cl ions will start getting produced. Is that clear? Because all the Cl2 will start gaining electrons, and they'll start turning into Cl ions. Is this clear?
Yes, sir.
As a plus, again, it's not going to happen endlessly. There would come a point when the positive charge becomes so large that positive charge will take the Cl ion and start pulling electrons back from it. So it will be gaining electrons up to a certain point. At a certain point, the platinum becomes so electron deficient that it sees the Cl ions and starts pulling electrons away from it. So at that point, it's going to eventually become reversible. And all you have to do is you just have to connect this with a voltmeter. That's it. And measure the voltage. Okay, that's it. So you're just going to connect it with a voltmeter and measure whatever the voltage is. And in this case, the E naught comes out to be very positive. It's 1.36 volts. So because we know that Cl really likes to gain electrons, so the electrode over here will become very, very electron deficient. Okay, but the important thing is that you should know how to make this electrode. Whenever there's a gas, this is the diagram of that electrode. Is that clear? ये clear है सारों को? ठीक है. Zaira, is this clear? Jody,
Yes,
is
sir.
this okay? Akshita, all clear, right?
Yes, sir.
Achha, so that's one thing. Let's do the third one. There's another type of electrode, that's part C. What if you're investigating who wants to gain electron, who wants to lose electrons, and they're just ions? If your solution only has, if you're investigating only aqueous ions only, so you want to figure out. Take it just 1 second. I said, so you want to figure out let's say this is the thing that you're trying to figure out. If Fe3 plus, does it like to gain electrons and turn into Fe2 plus? Or the reverse, does Fe2 plus like to lose electrons and turn into Fe3 plus? So how would you figure out whether it likes to go in the forward direction, it likes to gain electrons, or does it like to lose electrons? So how can we figure that out? So if it's only aqueous ions, that's an easy one. What you're going to do is you'll have a solution, and you're going to dump all those ions into the solution, Fe3 plus, as well as Fe2 plus. Just mix them up. But remember, they're going to be 1 mole per dm cube each. So I've added all of them into the solution. Now, again, there's an electrode that's missing, because if Fe3 plus decides to gain electrons, like if Fe3 plus has a very strong tendency to actually gain electrons, where would those electrons come from? So you need an electrode. So what you're going to do is you're going to add a platinum electrode. Okay, so you're going to add a platinum electrode. I'm going to throw chota kar lete hain. One second. So we've added a platinum electrode. And let's connect this with a wire and with a voltmeter. So voltmeter and your reference point. So let's say if Fe3 plus likes to gain a lot of electrons. So what will happen to the electrode? It will become very, very positive, because Fe3 plus is going to come to the platinum electrode and start gaining electrons, and it will start turning into Fe2 plus, right? So the platinum electrode would become very, very positive. Vice versa, if the reverse was true. I mean, right now I have no idea what it likes to do. But let's say vice versa, if Fe2 plus had a very strong tendency to actually lose electrons. So in that case, what's going to happen? What's going to happen is that a lot of electrons would accumulate on the platinum electrode, because the Fe2 plus would be losing a lot of electrons. So, but whatever happens, the potential builds up on the platinum electrode, and it eventually becomes or reaches equilibrium. And the E naught is already calculated. This one is 0.77 volts. So that's kind of positive. That's on the higher side. So that means this is more accurate. Fe3 plus kind of likes to gain electrons. That's why it's becoming more positive. Is that clear?
Yes.
Yes, sir.
Okay. So right now, the basic thing is the drawing. Aqueous ions only. If you have a reaction, if you have substances and they're all aqueous ions and you're trying to investigate, you just dump all those aqueous ions into the solution and you introduce a platinum electrode. If you have a gas, then what you're going to do is you're going to put a gas jar, and all the ions would be in the solution, and you need a platinum electrode in that case as well, an inert electrode. If you have a metal involved in the reaction, then it's easy. You don't need a platinum electrode because the metal itself can act as the electrode. So the ions would be in the solution and the metal would be placed. And if someone wants to lose electrons, it's going to make it negative. If someone wants to gain electrons, that's going to make it positive. The main thing is a higher potential indicates it likes to gain electrons, a lower potential indicates it likes to lose electrons. But the drawings over here are very important. I mean, you got a lot of marks for drawings. So 3 types of electrodes. We've done all 3 types of electrodes. So we're going to continue with this. We will continue this with the same thing tomorrow then. Is that clear? Any questions about this? Clear? Everything clear, right?
Yes, sir.
So then let's continue tomorrow then. Take care. Take care, everyone.
Yes, sir. Allah Hafiz.
Thank you.
Okay, thank you.